We are all well aware of the traffic situations, and we all look out for a way we can avoid these traffic situations so we can reach from one place to another quickly as soon as possible. Simulations basically give us a way out, and they help us avoid, and they give us precautions on where the traffic situation is really bad, so we can deroute and take alternative paths.
Often the models that are present today, they can be broadly classified into two categories. One is the bottom-up approach, one is the top-down approach. In the bottom-up approach, you start at a micro scale. That is, you start individual cars and vehicles, and then you scale up till you reach the whole network. Whereas in the bottom-up scale, you start at a higher level. Now, both of these, the drawbacks of the bottom-up approach is that although it's very accurate, it needs a lot of input data. That is, you need the whole origin destination metric. Whereas for the top-down approach, although it starts at a macro scale, you do not get the accuracy that you look for. This model tries to get the best of both worlds by combining these two approaches.
The method is split into 6 steps. The researchers began by a network representation. Now, the researchers availed the survey data, input data from OpenStreetMap. OpenStreetMap is basically a software which gives us a free editable version of the world map. Now, there are various libraries that are available within this. One of the major libraries are OSMNX, which is a Python package which helps in converting this input data into a represented form. Apart from this, there are various other libraries which gives us features regarding the roads. Like, it also gives us the details about the population densities. It gives us details whether the section of a road is a one-way or not, or whether there's a dead end, and several other features.
Once the network was modeled, this is how we compare the computer-generated model versus the Google Maps image of the city of Graz.
The researchers began by calculating or finding the shortest distance or shortest paths between two pairs of nodes. Now, it's not always necessary that the shortest path is always the fastest path. In order to get the fastest path in terms of the shortest path, we have a load factor, which we'll be seeing in the following slides. Since this procedure is highly time consuming, the input data is taken into consideration way before the simulation.
Also, another thing to note is that there are times when you want to have an alternative path, and if that time you recalculate all the paths between those two nodes, it will be really time consuming, and therefore before we start the whole procedure, we calculate all the paths within a certain distance, not just the shortest path, but all the paths within a certain distance of two nodes, and then store them in bins. This will make our real-time analysis more easier.
Now we come to the main question of how the researchers have availed the survey data. They took it from a paper called Osterbeck Antowex, which basically consisted of survey data regarding 18,000 respondents on 2 separate days, which gave them 36,000 days. Now, to improve accuracy, this data was truncated to 1,800 days, and also because since the investigated area is the city of Graz, so they restricted the data to 1,800 days.
Now, how did they do this? So basically, they use something called as a multi-agent approach, where each entity in the model is an agent. So you assign one agent to each person based on the population density of the city of Graz, which you get from the OpenStreetMap, and then we generate the trip schedule of each other person. Now, how do we generate a trip schedule? We have the behavior of every person who has gone through the survey. So, if we have 30% as doctors, then we generate out of every 100 agents, we generate 30 of them are doctors, and these tend to go to hospital at 9 a.m. in the morning. So, in this this process, we generate the whole trip schedule for each of the agents that we have placed in the city of Graz in our model. And one more thing that we can notice is that the ending point of the first trip of every agent is the starting point of his next trip.
The load factor A is nothing but the proportion between VH and CH. VH is nothing but the number of vehicles of that section of road, and CH is the hourly traffic capacity. Now, after the calculation of the load factor, it's subdivided into, it's basically divided into three categories, which gives us the nature of the traffic flow.
Now, once we get the load factor, we recalculate the shortest path by weighing them with the load factor. What is the load factor? Load factor just tells you how congested a road network is going to be. So now we recalculate the shortest paths by weighing them with the load factor in order to get the fastest paths. Also, another thing that we need to note here is that we know that in times of huge traffic, when you get suggestions of an alternative route, there are people who switch and people who do not switch. So to arrive at what percentage of people actually respond to these alternative suggestions and switch the path that they are going through, the researchers have referred to another paper known as D. Parma et al., which says that 30% of the commuters respond to these suggestions. Now, using this new information, we recalculate we repeat the whole process. The final but the most important part is the model actually representing the real world scenario? Is it accurate enough? Is it good enough for us to address the issues of traffic? So this what we have done is we have compared the real life scenario, the traffic on the roads, each of the roads, they compare them with the traffic in the model that we are generating. That is the load factor in the model versus the load factor that we get from the data from Google, and then try to see how huge the error is. T stands for relative time lost, where you have time at peak hours minus time on a general day by time on a general day. So this gives you the relative time lost. This is for the real life scenario. Whereas for the situation of the model that we have created, we have our load factor A. So now we subtract these two for each of the road networks, that gives us D. Then we calculate the D average over the whole day for each of the roads, and then sum it up. So this is our error for each of the roads. This is represented, now the error before we have included traffic jam avoidance. This is what it looks like, where red stands for positive error, highest positive error, and deep blue stands for the highest negative error, and gray stands for no error. So after including the traffic jam avoidance, if we recalculate the whole thing, we see that the percentage of gray in the whole map has increased a lot. To conclude, we find that this is a model that is way faster than traditional models, because although you need the origin destination data to improve accuracy, we don't need to use it always as input. We use the survey from mobility behavior, and from that we arrive at the origin destination matrix, which should not be a huge complex time consuming process as when compared to entering the whole matrix. Also, this is more relevant and it can be updated in different scenarios. For example, if a new industrial hub comes up in a different place, all you need to do is go into your mobility behavior data and add a new factor. And the problem that we face with this model is we have discretized in points of 1 hour, and this is still not real time. These are the following differences that we referred to in course of trying to review this paper. Any questions can be in the comments below.